Okay, so it's time for the first interesting theorem. So this is section 1.6, and it's called Lagrange Theorem. So that's a very interesting statement, and I will give you a somewhat unusual proof of this theorem, very geometric, combinatorial in a way, and I'm not going to do everything absolutely rigorously, so I'll use some ideas from graph theory, which are easy to make rigorous and intuitively obvious, but I'm not going to maybe get all bits here, though there will be another proof of this theorem later on in the course, which will be absolutely precise. So here is a statement. So theorem. So let G be a finite group and A inside G is some element. So for A inside G, there exists n for A inside G, we have A power the number of elements in the group equals to the identity. So if you take an element in your group and multiply it on itself the number of times which equals to the order of the group, then you get identity. It's a finite number because the group is finite. And also we can say moreover, the order of G divides the order of the element. So that's, to be honest, not a very often used notation in the US. So that's the same thing as maybe more standard notation is order of A divides the order of G. So this is a Russian one, which I'm very used to. So at least sometimes I will definitely use it. So, so this is the main statement. And actually, we'll prove this stronger statement. And of course, so if you know that you know that A power order of A equals to the identity, and then if you know the second statement that order of G is order of A times something, so if order of G equals order of A times K, then of course A power order of A power K is equal to A power order of G. On the other hand, it's E power K, which is E. So this is why the statement starting with moreover is stronger than the original statement. So I'm going to prove that. Okay, so proof. By the way, so before I prove it, let me just remind you that we already looked at Z over 10Z, and orders of elements there were 1 for 0, 2 for 5, 5 for 2, for instance, and 10 for, say, 1. So all of them divide the order of the group, which is 10. And also we saw that if you take S3, the order is 6, and orders of elements are just 1 for identity, 2 for symmetries, and 3 for rotations, and no other orders appear, and all of them divide 6. So that's an interesting statement, and it's beautiful. It's non-trivial at all. Let me prove it. So proof uses the following idea. So I want to associate to a group a certain picture, which is called a graph. So let me quickly remind you what a graph is. So just reminder about graphs. And I will do it a bit informally. So if you don't know that, if you have never heard the word graph, you definitely need to Google it or just read somewhere in more detail what I'm talking about here, but let me give you some brief introduction. So what is a graph? So a graph, gamma, is a pair consisting of a set of vertices and set of edges. So why I write it in this way? Because there is a standard definition, but actually there are variations. So let me first draw a picture. So typical graph we represent as a set of vertices, some points, and then edges are basically connecting vertices, something like that. And usually when you draw a picture of a graph, then you don't, when you have two intersection of two edges, you don't think that there is additional point here. So it's just a way you draw it. So this graph is the same as if you draw this edge maybe going upwards. Okay, so how to define it formally? So set of vertices is just some set V, and set of edges, one way to say is that E is just any subset of V times V. So just every edge is just a pair of vertices, beginning and end. So that's not exactly the picture which I drew here, because here my edges don't have orientation, and if you think of an edge as just an element inside V times V, definitely there is a first and second vertex. So a pair gamma of V and E, where E is a subset of V times V. So this will be called probably oriented graph with loops. And the reason is that actually, if you draw it, let's imagine we have like 3 vertices, and then you want to draw the picture. So firstly here, every element of V times V is a pair, and you can draw it as an edge with an arrow, and that can be the picture. Also, for instance, a pair 3, 3 will correspond to an edge which looks like a loop. So this is why this is an oriented graph with loops. But if you want to define a picture like that, you can, for instance, say that these are edges, and edge is a pair of V times V, but you identify pair AB and BA, and then you will kind of get rid of this orientation, and so on. So what I don't want to do in this course, I don't want to go through these old definitions of graphs and discuss all the details there, but instead I will rely on this intuition with pictures. But one can actually easily fill in all the gaps. Okay, so now my main idea is to a group G and an element A, I will associate a certain graph. And this graph will actually explain what multiplication on A looks like. And then we will study this graph. Okay, so consider the following graph. So graph will be exactly this oriented graph, vertices, edges. So here vertices are just elements of the group. So basically my picture will be like that. I have G1, G2, and so on, sort of Gn. These are elements of my group, and these are vertices. And then I say that a pair G1, G2 is inside E if and only if G2 equals A times G1. So let me explain what it means in a more easy language. So let me erase this picture. I will just redraw it. So the idea is as follows. So we start with some element, for instance, E. And then according to this rule, there is exactly one edge going inside of E. You connect it with A times E, which will be A. And this is a oriented edge. So then I draw another oriented edge by multiplication by A. I get A squared, and so on. But also I can start with any other element G, and there will be an edge going outside, which will be multiplication by A. Another edge will be multiplication by A squared, and so on. So basically, for every element of a group, I draw exactly one edge going out, and this is the one which is obtained by multiplying on this element A. So this is what my graph is: a pair of the set G and the set of edges from every element of G. There is exactly one edge going out. Okay, so observation number 1. So observation. So for every vertex of gamma, there exists a unique, this is uniqueness, right? Edge going in and out. So why so? Because if you take an element G, so according to our definition, the only element inside the set of edges which has as the first element G will have A times G as a second one. So there is just one arrow going out. And simultaneously, if you know G2, G2 is G, so, if you know G2, which is G, then the only way to obtain G2 as A times something is to multiply A on A inverse G. So the only incoming edge goes from A inverse G. So what might happen? These two vertices might be the same. Moreover, even this AG might be the same as G, which is allowed in a graph. So I can say that, just a remark, is that G, sort of a picture like that, where you have G equals to AG, of course would imply that A is the identity, which is kind of boring case in terms of our theorem. And if, for instance, you have a picture like this, then it means we have G, AG, and this is A squared G, and this will mean that A squared equals to identity. So those are just two examples maybe of what this picture might look like. Okay, so then there comes a statement from graph theory. So imagine you have this graph, and this graph has this property. So for every vertex, there is exactly one edge going out, there exists exactly one edge going in. Maybe the same edge. So then there is a very simple corollary. So gamma, so observation 2, is that gamma is a union of non-intersecting oriented cycles. So again, I'm using here some definitions from graph theory, which intuitively that's clear. I will explain in a second what a cycle is. But formally speaking, you might want to look up the definition. So a cycle is just a sequence of vertices where you have, a vertex, an edge going out, a vertex, an edge going out, an edge going out, an edge going out, and so on. So just a sequence of, like a path, like a way you go from first vertex to second, third, fourth, and so on. And one can easily define what a cycle is. Non-intersecting mean they have different vertices, and union means that the gamma is just, this bunch of cycles, and there is no interaction between them, no edges between two different cycles. So the proof is almost a tautology. Let me erase now this formulation of a theorem and formulation of this graph definition, and then I will continue. Okay, so let's just understand why this is true. So you have your graph, you start with some vertex, the first one, and then you draw an edge going out. We know that for every vertex there is one edge going out. And then for this vertex there is also another edge going out, and so on, and you just continue going. So you continue going until you hit a vertex which you already saw here. So, and then you just, this will happen because your group is finite, so graph is finite, so you cannot go on forever. At some moment you will hit already a vertex which you have come across. But then notice that it basically, a picture like that can never happen because it means that the vertex you hit actually has two incoming edges, which cannot happen. So the only way it can happen if you actually hit again the vertex where you started with. And then you have this kind of a cycle, so this is exactly what is called a cycle. And the cycle has a property that for every vertex, you know that there is exactly one edge going in and out. And so definitely all other graph is not connected to it. There will be no edges going in or out from the cycle. And then you can start with some other vertex, and you can do the same thing there. And at some moment you will hit again your original vertex. And so your graph looks something like that. So this is gamma. And you can just present it as this union. And maybe the cycle can be short as just, one edge. So that's a second observation. And what is beautiful about this approach to proving the theorem is that we started with deriving a property of this graph from the property of the group. And then we immediately got a very strong corollary about what this group looks like using just graph theory. So there is no group theory here. And again, so the idea is that if this is element G, this is A times G, this is A squared times G, and so on. Okay. So now gamma is this union of cycles. So observation number 3 is that all cycles have the same length. And this length is just the order of A. So this is really simple, but we again need some group theory. So let's take some cycle. And it means we start with G, then we go to A times G, we go to A squared times G, and so on, until we go to G again. So let's write down here A power K G. So this is our cycle. And again, so the reason is that just because our arrow goes from G to A times G, so this is why it looks like that. So then we know that A power K plus 1, so the number of edges will be, let's say, K minus 1 here. So A power K will be times G will be again G, just because we know that if we go from this vertex to this one, you get back to G. Then A power K equals to 1. Okay, but then also we know that elements G, AG, and so on up to AK minus 1G are distinct, because otherwise it means that actually that's not a cycle. So these vertices are distinct by our construction. Otherwise we would kind of hit earlier. So then by cancellation, so remember there was this cancellation property a few lectures ago. We know that identity G and so on, A and so on, A power K minus 1 are distinct. So why? Because imagine two of them are the same. Actually, we don't even need constellation. Then multiplying by G, you get that two of these guys are the same. So they are all distinct. And then it implies that K is just by definition the order of A. So it is a number such that integer, positive integer, such that a power k is identity, is 1, and all previous elements are distinct. So all previous powers are distinct. So it means k is the order of a. But then we know that our group is a union of not intersecting sets, all having k elements. So then the order of G is order of A times the number of cycles. But this is exactly what the Lagrange theorem implies. So it means that order of A divides order of G, and A power order of G equals to A power order of A power number of cycles equals to the identity. So this is the end of the proof. So again, what we did, we started with defining a special kind of combinatorial object called a graph, starting with our group and element A, and this graph actually tells you what happens when you multiply on A. And then we first understood that because of the simple fact that there is one ingoing and one outgoing edge for every vertex, our graph is a union of these cycles. And then we said, okay, let's look at each of them. And each of them has the same lengths, being the order of A. And so all of them actually look absolutely the same. And then, of course, the number of elements of gamma, number of vertices, is the number of cycles times the length, the number of vertices in the cycle, which is the order from where the theorem follows. Okay, so I think it's rigorous. I didn't use anything non-trivial from graph theory, but later on we will have another theorem, which is a slight generalization of this one, where we will actually introduce a notion of a coset of a group relative to a subgroup, and this cosets will be exactly these cycles in our example, and the theorem here will be the order of G equals to the order of a subgroup times the number of cosets. So it's actually the same proof. Okay, so here we end this somewhat more complicated section, and maybe in the last section I want to say a few words about history of group theory and maybe add several examples.